Hi everyone, welcome to Lecture 6, The Stars. We are finally ready to move outside of our solar system and to start to talk about some of the wondrous aspects of the universe as opposed to just planets and our sun, which are wondrous in and of themselves, but now we can, in an abstract way, venture out very far into the universe. In this lecture, we're going to talk about the stars in a very general way. I'm not going to go through stars one by one, but I will talk about how we measure distances to stars, which we actually talked about a little bit. I will talk about how we categorize stars, which as it turns out is via their spectra. And we talked about spectroscopy a little bit in a previous lecture. Then I'm going to talk about, will I just quickly remind myself of the slides. Then we're going to talk about how we categorize stars via their brightnesses. Maybe I shouldn't use the word categorize, but how we describe stars via their brightnesses. And I will talk about two different concepts related to brightness. I will then discuss the inverse square law as it pertains to the brightnesses of stars. I will discuss with you the relationship between the luminosity of the star and the radius and the temperature. And then finally, we will introduce what's called the Hertzsprung-Russell diagram, the HR diagram. Let's first start by talking about the distances to stars. This is somewhat of a review since we talked about stellar parallax. Let's just introduce this term astrometry. I believe that I did use this term earlier in one of the lectures, but anyway, let's just introduce it here. Astrometry is the science or practice of determining distances and positions of stars. We can also say the speeds of stars as well. Anything that has to do with where stars are, where they're going, how far they are away from us. This problem of finding distances to stars is very difficult to solve, and we won't have a chance to talk about this problem fully in the lecture because we don't have enough time, but I do want to talk about distances to very nearby stars. This principle of stellar parallax allows us to compute the distances to stars that are maybe a few thousand light years away. We talked about parallax earlier in one of the lectures, as I mentioned, and I showed you how to get the equation that we use. I would like to show you another method, which is perfectly equivalent, but it's a slightly different interpretation. Here is the star that we're trying to measure the distance to. I drew an analogous diagram to this in a previous lecture. The difference here is that the star is not to the right, it's above, but it's otherwise exactly the same thing. Remember the concept of parallax. Parallax is the apparent shift in the position of an object due to looking at that object from different perspectives. The classic example is if you look at the world through your right eye versus your left eye. You can hold up a pen or your finger, let's say at arm's length from you, and if you stare at the tip of the pen or your finger with your right eye with your left eye closed and then switch and go back and forth, you will notice that the tip of your finger or the pen will appear to shift. And it's best if you put the tip in front of an object that's identifiable, like the corner of a room, for example. And it's better if you actually choose a faraway object as a reference point. So choose the corner, the opposite corner of the room that you're in, for example. Remember, this is an apparent shift. What's happening is that you're looking at the tip of the pen from the right side of your face and then the left side of your face. We can use this same principle to measure the distances to stars because we orbit the sun. And so that's sort of like having two eyes in a way, because we can stare at the stars from the so-called left side, if you want to put it that way, let's say in January, and then we can wait 6 months and we can stare at the stars from the so-called right side, This is analogous to looking at the world from the left and right side of your face, singular. When we are staring at the star in January, we look at it in this direction, and then in July we look at it in this direction. The star will appear to shift, therefore, over the course of this 6-month period, and this shift is called the parallax angle, which is usually symbolized with a theta. If I were to use the trigonometric function theta, the trigonometric function tangent in this triangle here, then what I will get is tangent of theta equals the opposite side, which is 1 AU, divided by the hypotenuse, which is basically d. D is the distance between the sun and the star that we're interested in. And by the way, the distance between the Earth and the sun on average is 1 AU. That's how we define it. So that gives us this equation here, and tangent is a trig function. You don't have to know trigonometry for this course. I'm just introducing you to a second way to think about the parallax equation. This is another way to derive it, but you're not going to have to ever use tangents in a problem, for example. The only reason I'm introducing it here is because when the angle is really small, when theta is much, much smaller than 1 degree, let's say, tangent of theta is about equal to theta. This is a well-known approximation in trigonometry. So we can replace this tangent of theta with just theta, then we can rearrange it and we get this. And you'll notice that this is exactly the same equation that I had before in a previous lecture when I talked about stellar parallax. So this equation down here that I'm checking with a blue check, this is the stellar parallax equation. Theta is measured in arcseconds. 1 arcsecond is 1/3600th of a degree, And up here we have 1 astronomical unit, 1 AU, as I said, and then D is measured in parsecs. Remember that this can only be used to measure the distances to very nearby stars. By very nearby, we mean a few thousand light years, which is very far, but actually, compared to the size of the universe, that's actually relatively close. It's very far in the sense that we cannot get to those stars. I want to say one more thing, which is why this equation is only valid for close stars. Theta is very small for all stars in the universe because all stars are very far compared to the sun, all stars other than the sun. And the farther away a star is, the smaller this angle is. Imagine taking this star and moving it backwards. So take this star and imagine that it's miles and miles away. This angle here would be really, really small. So you might wonder, well, why shouldn't the stellar parallax equation be even more accurate for very far away stars? Because after all, we're assuming that the angle is small. And the farther away a star is, the smaller the angle. Well, the problem is that for stars that are, let's say, 20, 30, 50,000 light years away or farther, the parallax angles are so small that they're not really measurable with any accuracy, with any in a way that gives us some assurance that they're accurate. I couldn't quite put that in a full sentence, but yeah, we cannot measure those angles accurately. Okay, so moving away from that highly inarticulate statement, hopefully it's clear now why stellar parallax is only valid for relatively close stars. Let's talk about some units. I actually mentioned most of the stuff. 1 parsec is the distance of an object whose parallax angle is 1 arcsecond. I mentioned that earlier. 1 arcsecond is equal to, 1 parsec is equal to 3.26 light years. I had mentioned that, I think, in a previous lecture. This is just a review. This is a good thing to know, the conversion between parsecs and light years. Let's give some sense of how large a parsec is. One of the themes in this course is scale, and I've mentioned to you how we find distances to stars, and I've given you numbers like a few thousand light years, etc. But what does that really mean? Well, our Milky Way galaxy, which contains probably several 100 billion stars, which is the galaxy in which we live, is about 31,000 parsecs wide. Actually, there's a debate about how wide it is, but it's roughly around 100,000 light years across, or wide, which corresponds to about 31,000 parsecs. Our nearest spiral galaxy neighbor, I said galactic neighbor, but I mean major galaxy. There's some minor galaxies closer, but the nearest major galaxy to us is about 780,000 parsecs from Earth. So we're talking about a distance that's greater than 10 times the size of the Milky Way galaxy. All right, and then I said this. This is it for the distances to stars. Let's move on to spectroscopy, which is also a review, but then we're going to apply it to the concept of categorizing stars. Remember that a spectrum of an atom is a list or representation of all of the wavelengths of that atom that it can absorb or emit. And the reason that atoms can only absorb or emit very specific wavelengths is because atoms are not like little solar systems. They behave in a different way. If this center black circle here is the nucleus, then I can draw electrons here in these different orbits. So suppose we have one electron here, which is blue. This is not to scale. Another electron here, which is, sorry, let's not say another electron. Let's just have one electron. So one electron in blue here. And let's say that I want to move this electron from the inner red circle to the outer red circle. The technical terminology we use is the ground state. That's what the inner red circle is. Right, so this is the ground state, and this is the first excited state. We should start to use the jargon. So we want to move the electron from the ground state to the first excited state. This is nothing more than the inner orbit to the outer orbit here. And in principle, there's more orbits, but let's just focus on two. In order to do so, we have to shine light on this electron that has a very specific wavelength. That wavelength will correspond to the energy difference between these states. Each state has a certain energy level, or more specifically, the electron has a certain energy if it's in a certain state. So the ground state corresponds to a certain energy, the first excited state, etc. The energy difference between the states is precisely equal to the energy of the photon that you have to shine on the electron. So in other words, you have to give the electron exactly the right amount of energy to move up to the first excited state. If you give the electron 99% of the energy it needs to move to a higher state, nothing happens. This is not like a solar system. This is not like the world that we are used to. If you have to push a crate along a floor, let's say in a warehouse or something, you need a certain amount of energy, let's say, to push it from point A to point B. You're trying to get the crate to point B from point A. If you give the crate 99% of the amount of energy it takes to move it to point B, you will almost get to point B, right? Everyone knows that, right? Or if you give it half the amount of energy, you will get halfway there. Electrons don't behave like that. They're either at point A or they're at point B. There is nothing in between. This sounds strange, and it is strange from the perspective of creatures that live in the world we live in, which we call the classical world. So we don't interact with electrons on any kind of personal level. Of course, there are electrons all around us, but we don't shine light on electrons and try to move them up to higher energy levels on a daily basis. But if you actually study the light that can be absorbed or emitted by an atom, you will see that there is a countable number of wavelengths that the atom can emit or absorb. And those wavelengths correspond to energy differences between the states. That was my quick capsule review of where atomic spectra come from. This is why atoms don't just emit any old wavelengths of light. If you're still confused by this, please go back to the lecture on light and telescopes, where I talk a bit about light and also atoms. Let's move on now to excuse me, how we classify stars, because really we want to take this idea of spectra and we want to apply it to stars so we can actually do some astronomy instead of talking about atoms all the time. In order to classify stars, we look at their spectra. The spectrum of an atom is referred to as an emission spectrum because the idea is that you would heat up the atom, or in principle many atoms, or in practice many atoms, and then the electrons in those atoms would get excited. They would move up to higher energy levels because you heated them, give them energy. When those electrons fell back down to lower energy levels, then they would emit electrons. That gives rise to an emission spectrum. I might as well show you what it looks like here. This still is a review, right? So this is an emission spectrum. The spectrum of a star does not look like this because the cores of stars produce massive quantities of all kinds of radiation, but you won't see the full spectrum, the full electromagnetic spectrum from a star because stars have atmospheres. The atmosphere of a star will contain specific elements: hydrogen, helium, iron, potassium, all that stuff, and more. And those specific elements will absorb specific wavelengths of light. Therefore, what we get when we study the light from a star is what's called an absorption spectrum, which looks like the full electromagnetic spectrum, all the colors, etc., and X-rays and radio waves, but with very specific wavelengths that are cut out. These wavelengths that have been cut out are called absorption lines, or bands sometimes. And these lines correspond to, as I said, specific wavelengths of light that are absorbed by whatever atoms are in the atmosphere of the star. And this gives us a chemical fingerprint, therefore, because we can then we can then compare these absorption lines to the known absorption lines for atoms, and we can figure out what's in the atmosphere of the star. And if we classify stars based on their spectra, because it turns out different stars have different spectra, then we get what are called spectral classes. And this is how we categorize stars primarily. There's also a continuous spectrum, by the way, which just means all the different wavelengths of light, the continuous distribution of wavelengths. Let's finally get to the spectral classifications of stars. Or there's really one primary classification system that we use. I'm sorry that the letters here are not in alphabetical order. I shouldn't be sorry, this is not my fault. It's just an historical accident, but we don't use A, B, C, D, etc. We use O, B, A, F, G, K, M, and then the latter two, L and T, are kind of minor classifications. So unfortunately, you're going to have to remember this series of letters in order, and one mnemonic you can use is "Oh, be a fine girl, guy, kiss me." It's a strange one. I didn't come up with it. This is the standard mnemonic that you'll find. If you Google it, it's in the book as well. You can think of another one if you don't like this one. However you choose to remember it is fine. And to make things a little bit more confusing for you, this classification is really a classification of surface temperature. So there's two things going on here. One thing is that we have these different classifications, O through M, and then L and T are, as I said, minor ones. So we'll mostly focus on O through M. And these classifications are based on the different spectra of stars. You will study the spectrum of a star. You will classify it based on what the spectrum looks like. We will talk about that. And then you give the star, based on that classification, a letter. Each letter corresponds to a different classification. And there's another thing going on, which is that this classification also is basically the same thing as classifying the surface temperature of the star. And this is confusing for reasons I will mention, but hopefully when I explain it, it will be less confusing. The Sun, by the way, is a G-type star. I just want to get that out there because that's a basic fact you should know. Let us talk about first what the different spectra look like for the different classes. And then we will get to this problem of this classification really being a temperature classification. This is a little bit of a misleading figure from your book. But even though it's a little bit misleading, it's still good because it is colorful and it allows you to look at all the different classifications, and this does give you a decent representation of what the spectra look like. It's a little bit misleading because sometimes students will look at one of the spectra and they think, okay, this is exactly what it looks like. But as you may have noticed, if you looked at, for example, the spectrum of the Sun, which is in your book, or actually it's just a snapshot of some portion of it, it's not the whole thing. Stellar spectra are very complicated, and so there's really no way to describe in a course like this all of the different characteristics of any spectral class. So what we're going to do here is give a very basic overview. And here's the best way to think about it. I mentioned earlier I'm just going to talk about the spectral classes and then put the temperature thing aside. Actually, I think it's best to do this simultaneously. I think it makes it easier. Let's just start with the idea of an O-type star. I'm going to do this in red to make it more obvious. Right? So this is an O-type star. This is at the top. And the reason it's at the top is because this is the hottest kind. I misspelled hottest here. This is the hottest kind of star. And I'm always talking about the surface temperature, by the way. Let's put aside the temperature of the core and convection zone, etc. We're just talking about surface temperature here. So these are the hottest kinds of stars. And down here we have the M-type. Remember there's L and T, but those we're mostly not going to worry about. Those are pretty minor. And then these are the coolest. So this is a relative scale. Even the cool stars are pretty hot, but O-type stars are very hot indeed. The cutoff temperature is around 30,000 Kelvin. Now, O-type stars have very weak hydrogen lines. This is something that you're going to hear me say quite a bit. Remember, we talked about absorption lines. These are specific wavelengths of light that are absorbed by whatever's in the atmosphere of the star. Hydrogen has very specific lines. There's many lines hydrogen has. These are all the different wavelengths that hydrogen can absorb. And you'll notice here, this is one thing that makes this diagram a little bit misleading. You'll notice here that these lines are pretty noticeable. These are all hydrogen lines here that I'm highlighting. But actually, O-type stars have weak hydrogen lines. That means that the lines are there, but they're not very dark. That's what we mean by weak. We mean that you can notice them, maybe, but just barely. And that's actually not very clear based on this diagram. But in any case, that is indeed true. And the reason why O-type stars have weak hydrogen lines is not because there's not a lot of hydrogen in O-type stars. It turns out that all stars, for the most part, have the same stuff. Not exactly, there are differences, but the differences are pretty minor. So overall, to first approximation, roughly speaking, all stars have the same constituents. Mostly hydrogen, some helium, and then some other stuff, which we call metals. Now this might sound confusing to you because I just said that the different classifications here correspond to different spectra. And the spectrum of the star tells you what's in it. So how can all stars pretty much have the same stuff if they have different spectra? And the reason is because stellar spectra are affected by the surface temperature of the star. This is a good example. O-type stars have plenty of hydrogen. The reason why the hydrogen lines are weak in O-type stars is because O-type stars are so hot that most or almost all of the hydrogen in their atmospheres has been ionized. By ionized, what I mean is that the electrons have so much energy that they just leave. They get up and leave the atom. I'm trying to draw an atom here, I'm sorry. I cannot draw an atom properly. This is the nucleus. This is one orbit. This is another orbit. So here is an electron. If I were to heat this hydrogen atom, I can move the electron to a higher energy level. I talked about that earlier. If I were to heat it to 30,000 Kelvin, let's say, the electron would have so much energy it would just leave. There's a minimum amount of energy you have to give the electron to actually remove it completely. Once you remove it completely, you don't really have an atom. You just have a nucleus, which is, in the case of hydrogen, just a proton. So there's no electron to absorb light. And so therefore, this atom does not give you a spectral line. The electron cannot absorb or emit radiation if it's not there. And this is what's known as an ionized hydrogen atom. This is what we mean when we say it's ionized. It's missing an electron or all of the electrons. So if something is completely ionized, it's missing, by something I mean an atom, is missing all of its electrons, that object is actually not really an atom anymore, it's just a nucleus, and therefore it will not correspond to any spectral lines. So this is a roundabout way of saying that the surface temperature of a star determines the state of the atoms in the atmosphere, in the surface. And this actually gives rise to different spectral classes. So this is how different stars have pretty much the same stuff in them, but they give rise to very different spectra. Let's just go through the spectra somewhat quickly and talk about the overall characteristics. There'll be an activity on this which hopefully will make this more clear. This is the kind of topic that you have to sit down and work at in order to understand. So hopefully the activity, well, maybe I don't want to be pessimistic. Maybe you'll understand it perfectly at the end of this lecture, but if not, the activity will help you. So I told you that O-type stars have weak hydrogen lines. They sometimes have strong ionized helium lines. We're talking here about partially ionized helium, meaning an electron's been removed, but not all the electrons. O-type stars don't really have any other lines for the most part. And the reason is because it turns out that hydrogen is hard to ionize, just because of the physics of the hydrogen atom. And the details of that don't matter for our purposes. Metals in particular are easy to ionize. This is something that you need to know. So iron, for the purposes of astronomy, oxygen is a metal. Carbon is a metal in terms of astronomy. Anything that is heavier than hydrogen or helium is a metal as far as astronomers are concerned. If you go to a chemistry person, they will tell you that you're crazy. But anyway, we're going to stick to the astronomy convention and refer to carbon and oxygen, etc., as metals. So metals are relatively easy to ionize, especially things that are typically called metals in a non-astronomy context like iron. Everyone knows iron's a metal, right? And therefore, the hottest stars don't have any of those spectral lines because all of those atoms have been ionized. So there's iron in O-type stars, but it's all been ionized. So you don't see any of those spectral lines. As you go down the list toward cooler and cooler stars, you start to see first ionized metals, because you start to see metals that are partially ionized. That's what if we talk about, sorry, let me just back up a second. If we talk about the absorption lines of ionized metals, we're talking about metals or metal atoms that are partially ionized, meaning they've lost some of their electrons. And those atoms will give rise to different spectral lines than what we call neutral metals. A neutral metal is one that has all of its electrons. So it's not charged. It hasn't lost any of its charged particles. So we start to see, I'm going to give you a broad overview here. We start to see ionized metals. Not in O-type stars, but as we go down toward the cooler stars. And then we start to see neutral metals in particularly in F-type stars. And F-type stars are very prominent. We have a lot of neutral metals as well as ionized metals. And then same thing with G-type stars. And then as we get down to K and M-type stars, we see primarily neutral metals. And sometimes we can even see molecules, but only in the coolest stars. So that's a very broad overview. I know that it's maybe not as thorough as you would have liked, but the first thing I want you to do is think about the reasons why you see certain spectral lines and not others. So try to think about hydrogen's hard to ionize, metals are easier. So as you go down the list toward cooler and cooler stars, you start to see ionized metals and then neutral and then even molecules. Molecules are very easy to break up. Relatively speaking, if you take well, you know this if you burn yourself, right? That's basically what a burn is. You're made of molecules, and if you touch a hot pizza plate, you'll burn yourself. So molecules are easy to actually destroy via heat. So you only see molecules, therefore, in the very coolest stars. Let's talk about some of the more specifics. I have a table in the next slide that gives some more specifics here. I mentioned to you that some of the surface temperatures are different a little bit because they're slightly different definitions. These definitions don't matter very much. What really matters is you understand the concepts and also you know the letters, the classification scale, O through M, and then L and T. So I told you that I'll get to that in a bit. I'll get to the color in just a moment. O-type stars have weak hydrogen lines. They also can have ionized helium lines. B-type stars have prominent neutral helium lines. They also have stronger hydrogen lines. A-type stars have particularly prominent hydrogen lines. F-type stars have noticeable metallic lines. You start to get ionized and neutral metals here. Same with G-type stars. K-type stars are dominated by metallic lines, primarily neutral metals. And then in M-type stars, we even get some molecular lines like titanium oxide, which is a metal. So these characteristics here are not completely thorough. These are just some of the characteristics, but hopefully this gives you a decent overview. Okay, so this wasn't as thorough as maybe I had promised, but I do want to go through this color aspect here. I always tell the following story to students. Whenever I go into a hotel and I look at the bath tap and I see red corresponding to hot and blue corresponding to cold, I get a little bit annoyed because actually that's backwards. The hottest stars are blue and the coolest stars are red or even brown. And this is actually not a convention, this is the way it works. And we know this because blue light has more energy than red light. We talked about that earlier on in this course when we did the lecture on light and telescopes. Red light has a longer wavelength than blue light, so blue light has more energy. Long wavelength means low energy. Very hot objects, like O-type stars, are going to emit light that has very high energies. They're going to emit, let me say that a little bit differently, they're going to emit different types of light, but they're going to be toward the higher energy end of the spectrum. So they'll tend to emit light with very high energy. That corresponds to blue light. Cool stars, on the other hand, are going to emit primarily red light. So red is actually cool and blue is hot. I do not know why people tend to think that the opposite is true, but anyway, when you go to a hotel, maybe in the future it will annoy you as much as it annoys me, and then you can complain and people think you're crazy, but you're completely right that it's backwards. All right, so anyway, you should know that O-type stars are very blue, and then M-type stars are very red. L and T are extremely cool indeed, and these are actually brown because they're so cool. Our sun is a G-type star, which is a white-yellow star, which you probably knew. right. This is a somewhat complicated topic, but we're going to move on from it for now, but we're going to revisit it when it comes to the activity, and hopefully with the activity and this subject will be clear, if it's not clear at the moment. Let's talk about the motions of stars, and then we will get to the way that we assess or measure the brightnesses of stars. Stars move in two basic ways. They have what we call radial velocities and then proper motion. Let's look at this diagram here. The book has given the example of Barnard's star, which is just one star in the universe, but this applies to any star. Stars can be moving toward us or away from us. This is known as the radial velocity. So this is the speed at which they're going away from us or toward us. And then stars can have a transverse velocity, which is the velocity of the star in the perpendicular direction. So not away from us or toward us, but in the sort of opposite direction, if you like. So left-right, you can think of it like that. I should say that proper motion in principle affects the position of the star on the celestial sphere. But the proper motions of stars are very, very small. It's typically less than 0.1 second of arc per year, which is not noticeable unless you have a very good telescope. So this is not really noticeable to your eyes, but nonetheless, stars actually do physically move with respect to Earth. Once again, I just want to point out, as I mentioned in the celestial sphere lecture, that when we say that stars move on the celestial sphere, we're actually talking about Earth moving around. So we're talking about stars moving on the celestial sphere in an abstract way, but it's actually Earth that's moving. Let's talk about the Doppler shift. How can we determine whether stars are moving away from us or toward us, or how fast they're going away from us or toward us? We can do this using the Doppler shift. The Doppler shift corresponds to the elongating or compression. That's the word I'm looking for. There we go. It's right in my slides. The elongating or the compressing of light as it is either as it's emitted by an object going away from us or going toward us. If I shine light in your direction and I move toward you very quickly, so imagine I have a flashlight and I'm running toward you, then that light will be compressed as it goes from the flashlight to your eyes, and it will look bluer to you than it does to me. This is referred to as a blue shift, and the reason it looks bluer is because if you compress the wavelength of light, you therefore make it bluer, because blue light has a smaller wavelength, a higher energy than red light. And ditto for the red shift, except it's the other way around. It's stretched out, and this corresponds to light being emitted by an object that's moving away from you. It turns out that almost all galaxies in the universe, therefore almost all stars in the universe, are moving away from us, for reasons we will talk about later on in this course. So redshift will be a very important concept when we get to cosmology, when we study the universe as a whole. So how do we determine if a star is moving toward us or away from us? Well, we have to look to see whether the light from it is redshifted or blue shifted. Well, how do you know that? Because we know that there are some stars that are bluer, some stars that are redder, some stars that are yellow. What we do is we study the spectra of stars. We can classify the star via its spectrum, and remember that the spectrum of a star gives us a chemical fingerprint. It tells us what's in the star: oxygen, iron, hydrogen, etc. So we match up the spectral lines. So I just want to point out these lines. We match up the spectral lines here to spectral lines that are known for the various elements. And then if a star is redshifted, then all of these lines will be shifted over by the same amount. I cannot do a good job drawing it but try to, excuse me, try to stare at this diagram here. This is the lab spectrum. So that means that this is the spectrum in the middle here that we would expect from a star. This is an arbitrary star, if it weren't moving toward us or away from us. But of course, stars are moving, but this would correspond to what we would expect if the spectral lines matched exactly with what we get from the chemical elements. So in other words, let's say there's a line at 450 nanometers. That's a wavelength of light. Maybe that corresponds to this line. I'm just making up a number. This corresponds to some atom. I'm not going to pick an atom. I don't want to pick one because it'll be wrong. I'm just making up numbers. But the point is that this is some line from some atom. And in reality, we're measuring, let's say, the top one here. This is, let's say for the sake of argument, a real star, and it's redshifted because it's moving away from us. So we will notice instead a spectral line at, let's say, 451. Now, how can you tell that this isn't another atom? Well, the reason is because all of these lines here will be shifted by the same amount. So we look for a constant shift of all the spectral lines, and there's very many of them, in one direction. And it's exactly the same shift. Let's say in this case 1 nanometer. And that's how we determine that this star is redshifted. And by looking at the size of the shift, whether it's 1 nanometer, 10 nanometers, etc., we can figure out the speed of the star. Because the faster the star is moving away from us, the more redshifted the light will be. And exactly the same thing applies to blue shifted. It's just shifted in the other direction. Let's finally talk about the brightnesses of stars. You might think that this is a very easy thing. You just look at the sky and you say, okay, one star is brighter than another. But unfortunately, there's a theme here, which is that it's not quite as simple as it seems on its surface. For example, there is a star called Betelgeuse. I use this example a lot. Betelgeuse is a nice star. It's a very massive red star, and it's extremely bright. The amount of light that Betelgeuse emits is much greater than the amount of light our sun emits. When you see Betelgeuse in the sky, it looks like a tiny red dot. It looks like a star, right? If you look at the sun, it does not look like that. It's much brighter. You shouldn't look at the sun without a filter. It could damage your eyes. That's how bright it is. So how come? The sun appears to be vastly brighter than Betelgeuse, but I just told you that Betelgeuse is actually much brighter than the sun and much bigger. The reason is that Betelgeuse is hundreds of light years away. It's about 740-ish light years away, whereas the sun is very close. If you're outside and a firefly flies close to your eye, it might appear very bright for a very short period of time when it's right next to your eye. If you're staring at, let's say, a football stadium or baseball stadium or whatever that's very far away, the floodlights, or whatever they're called, I guess the stadium lights, that's the term, the stadium lights might seem less bright than the firefly. But it's not because the firefly is emitting more light than a stadium light. Obviously, those lights are brighter. But the stadium lights are much farther away. So we have to be able to distinguish between two different concepts. One is the luminosity, which is the amount of light that's actually emitted. Luminosity is sort of like the brightness rating of a light bulb. This tells you how much light the light bulb is actually emitting. And then the other thing we have to define here, in opposition to luminosity, is the apparent brightness. Apparent brightness is how bright an object looks. It's exactly what it sounds like. And the difference, of course, is that if you have a very, as I was saying earlier, if you have a very bright bulb, like a stadium light, that's very far away, it will appear to be dim. Let's take an astronomical example. The luminosity of Betelgeuse is much greater than that of the sun, thousands of times greater. Off the top of my head, I don't remember the number. But the apparent brightness of Betelgeuse is much smaller because it obviously looks dimmer since it's much farther away. Let's talk about why this might seem intuitive to you or obvious, but let's quickly talk about why stars that are farther away look dimmer. I'm going to skip ahead just one slide because I just want to get this out of the way at this point, and then I'll go back to the previous slide. In particular, what I want to do is explain to you why apparent brightness, which I'm going to abbreviate AB, is proportional to 1 over r squared. In other words, if let's say you have two stars, they have exactly the same amount of light that they emit. Their luminosity is the same, but one is twice as far away as the other. The star that's farther away will have a smaller apparent brightness. It will look dimmer, but it won't look half as dim. It will look 1/4 as dim. And that's because apparent brightness is an inverse square law. And I want to explain to you why that's true. Let's say that we have a light source, a star, and we are measuring the light from that star in 3 different locations. One location is at a distance of 1 from the star. This could be 1 astronomical unit. This could be 1 light year. It doesn't matter. So just pick a unit, and 1 unit of distance corresponds to this sphere. So this sphere is an imaginary sphere that surrounds the star, and we are on the surface of the sphere. We're a planet, or we're beings on a planet, and we have eyes, as you know, or we have a telescope. It doesn't matter. We have some kind of light collecting device. And that light collecting device has an area of 1 square. So whatever light comes from this star and passes through our light collecting device, let's say it's an eye, is light we will see. If there's light, which there is, that is emitted on the other side, we won't see that. It's emitted, but it's being emitted towards some other planet, so we don't even observe it. Now let's go to an orbit, let's say this is a solar system, for the sake of argument, that is a distance of 2 away. Let's say 2 astronomical units. That same light that once passed through 1 square is now passing through 4 squares. And the reason is that the surface area of a sphere is equal to, or proportional to rather, r squared. It should be proportional. So it's 4 pi r squared is what the surface area equals, but the point is that it's proportional to r squared. The constant there doesn't matter. So the surface area of this green sphere is 4 times greater than the surface area of this inner red sphere. It's just a law of geometry. So that means that the same amount of light that passed through 1 square will now pass through 4 squares. But our eyes are only 1 square in area. Our eyes haven't increased in size. And so therefore, we're actually not getting the same amount of light. Once we go to the second planet, which is a distance of 2 away, our eyes still have the same capacity to absorb light, so we're getting 1/4 of the light. And then ditto for this third one here. This is a distance of 3 away, so therefore the area increases by 9. So we're getting 1/9 of the light. So that's why a star that's very far away will look very dim. And this actually is an example of an inverse square law, because the amount of light that you're getting from the star actually decreases as 1 over r squared. Just wanted to get that explanation out of the way. That's a very nice example of an inverse square law, as I have said multiple times. That's an important concept, which is why I keep emphasizing it. But let's move on now to how we measure luminosity and apparent brightness. Let's start with luminosity. Remember, luminosity is the amount of light that a star emits. It's not how bright the star looks. We can measure brightness in different ways. We have a scale for the apparent brightness and then one from the absolute brightness. Luminosity corresponds to the absolute brightness, or the absolute magnitude, because the word absolute here means actual. That's what it means in this context. And luminosity refers to the amount of light the star actually emits. So it's how bright the star really is. Betelgeuse is really much brighter than the sun. It just doesn't appear that way from our perspective. Here on the left side, we have luminosity in solar units. So this means the number of suns that the luminosity corresponds to. If you have a luminosity of 1 in solar units, that means you emit exactly as much light as the sun. If you have a luminosity of 0.01, that means you emit 1/100th the amount of light as the sun emits. And if you have a luminosity of 100 million, then you're 100 million times brighter. On the other hand, on the right side, we have exactly the same scale, but we're using different numbers to measure it. This is called absolute magnitude, and this, I'm sorry to say, is a little confusing, because notice that this here is very bright. 100 million solar units is much brighter than 0.01. But notice that the absolute magnitude is negative down here and positive up here. This is just the way that the scale is defined. So a very negative absolute magnitude is a very bright star. Minus 25 on the absolute magnitude scale corresponds to around 100 million solar units, a very bright star. Positive 10 corresponds to a very dim star. The absolute magnitude has a very precise definition. It is the measure of the luminosity of a star if it were 10 parsecs from us. The 10 parsecs is really a convention, but the idea is the following. Stars are all different distances. Some are a few light years, some are 700, some are millions of light years away. Stars have very different luminosities, different actual brightnesses. What if we were to take, obviously this is impossible, but as a thought experiment, what if we were to take all the stars in the universe and line them up so they're exactly the same distance away from us, so that we can measure the brightnesses of the stars on the same level, so to speak. So in other words, you're not measuring the brightness of a firefly when it's right next to your eye and measuring the brightness of a stadium light when it's a mile away. You're going to put the firefly and the stadium light the same distance away from you. Well, you know what would happen. Obviously, you wouldn't even be able to see the firefly because the stadium light is so much brighter. So we're getting rid, in a sense, of the fact that objects that are farther away are dimmer. Now, obviously, we cannot do this in real life, but this is the abstract idea. So the absolute magnitude of a star is what the star, how bright the star would look if it were 10 parsecs from us. That's the idea. Now let's talk about apparent magnitude. Apparent magnitude is exactly the same thing, except it refers to how bright a star looks given its actual distance from Earth, rather than how bright the star really is. But everything I just said about the scale applies. So a very negative apparent magnitude is a star that looks really bright, and a very positive apparent magnitude is a star or an object that looks very dim. The sun has the smallest apparent magnitude of any object in the universe because it is the most apparently bright object. When the sun is out during the day, you can't see anything else. Sometimes you can see the moon, but the moon obviously is not as bright as the sun. So there's no other star in the universe that looks as bright to us as the sun, so therefore the sun has the smallest apparent magnitude. The full moon has a very small apparent magnitude because it's very bright. And then we have Venus, and then we have some stars, Sirius, Alpha Centauri, etc. As we go all the way up the list, we get up here to stars you can only see with relatively advanced telescopes. As I said, I'm sorry to say that this scale is a bit confusing because more negative numbers mean greater apparent brightnesses and also greater luminosities, but it's just something you have to get used to. I'll say one more thing, which is that these scales are actually log scales. And an increase, I'll explain what that means in a bit, but basically an increase in 1 in magnitude corresponds to an increase in brightness by a factor of 2.5, or a decrease, depending on what you mean by increase of 1. So as we go from minus 12.5 to minus 13.5, we have an increase in apparent brightness by a factor of 2.5. This is known as a log scale, and it doesn't really so much matter what it is. It's just based on logarithms. But we use this because the apparent brightnesses of objects differ by many factors of 10 and hundreds and thousands. Let's talk about how luminosity is related to the surface temperature and the radius of a star. The luminosity of a star is proportional to temperature to the fourth. I'm not going to try to explain where this comes from. This is a famous result in thermodynamics, but I'll just ask you to accept it. So if a star has, let's say, twice the surface temperature of the sun, its luminosity will be greater than the sun, all other things being equal, by 2 to the fourth. 2 to the fourth is 2 squared squared. 2 squared is 4. So 2 to the fourth is 16. So the luminosity of a star strongly depends on the temperature, with hotter stars being brighter. I think this is intuitive. A very hot object is brighter than a cool object. Luminosity is also proportional to the size of the star, in particular r squared. It's actually proportional to the surface area, but all stars are spheres, and the surface area of a sphere is 4 pi r squared. I think this also makes sense because stars that are much brighter than others should emit more light, because they're brighter, so they have greater surfaces from which to emit light. So hopefully the basic idea here is pretty intuitive, which is that the brightest stars are the ones that are the hottest and the largest. We can actually use these two facts that I've just underlined to figure out the luminosity of a star given the luminosity of other stars, and then information about the temperature and the radius. I just want to go through a quick example with you. Here we have 3 pictures from your book. These are 3 different stars. We have a what's called a blue giant, which is a very large blue hot star. Remember, blue means hot. Then we have a red giant, which is a large red cool star. And then we have what's called a red dwarf. We're going to get into these different classifications in the next section of this lecture. But for now, what we mean by red dwarf is a small cool star. What we mean by a red giant is a large red star, and by a blue giant, a large blue star. Let's say that we know that the temperature of star A is 4,000 Kelvin, which we do, and its radius is 1/2 that of the sun, which we do. So by the way, R with a little circle and a dot refers to the radius of the sun. This symbol here, the circle with the dot, refers to the sun. This is a very common notation in astronomy. The radius of this star, therefore, is 0.5 that of the sun. Its luminosity, I'm getting ahead of myself. So then what is its luminosity? Well, this diagram lists its luminosity as 0.05 that of the sun. So how do we know that? We can actually calculate that by knowing the radius and the temperature. I'll just do that calculation for you here. We know that the luminosity of a star is proportional to r squared. So we take 1/2, which is the size of this red dwarf in comparison to the sun. Its radius is 1/2, and we're going to square it because the luminosity is proportional to r squared. Then we're going to multiply it by the temperature to the fourth, we want to take the temperature of this star here and divide it by that of the sun. We want to take the ratio of the temperatures. So it's 4,000 Kelvin compared to 5,800 Kelvin for the sun. And if you multiply these numbers together, that gives you about 0.05. Right, so that's how we compute the luminosity of this star here, this tiny one, in comparison to that of the sun. And this would be 0.05 in units of solar, luminosity in comparison to the sun. So in other words, this star is 1/20th as bright as the sun. And you can do the same thing for stars B and C. I've done a little calculation here, but for the sake of time, I'm going to let you do that on your own. I want to move on now to HR diagrams. We've talked about how some stars are much hotter than others. Some stars are bigger than others. I've already mentioned to you an example of a star that's really big, Betelgeuse. In addition to categorizing stars based on their spectra, we also classify stars based on their sizes and temperatures based on what's called a Hertzsprung-Russell diagram, or I should say in what's called a Hertzsprung-Russell diagram. A Hertzsprung-Russell diagram actually classifies stars based on their luminosities and temperatures. Okay, I have to apologize here for a misspelling. I'm having trouble adding an extra L, but I always think that I have changed this, but for whatever reason I forget to change it. Russell has 2 L's, sorry. I know how to spell Hertzsprung-Russell diagram, I just always forget the L for some reason and never remember to put an extra one in. So it's Russell with 2 L's. Okay, so the Hertzsprung-Russell diagram is a way of categorizing stars based on their luminosities and also their temperatures. But this is also a way of categorizing stars based on their sizes and temperatures, because we know that the very hottest stars and the very largest stars are the most luminous. So let's just go toward, or get to, I should say, the diagram, Hertzsprung-Russell diagram. This is a depiction of the diagram. We have along the vertical axis the luminosity. Now, very often we're going to use the absolute magnitude scale. The absolute magnitude scale has negative numbers down here and positive numbers up here. Remember, I compared the absolute magnitude scale to the scale in terms of solar units. So they're equivalent, but we normally use absolute magnitude. I want to point that out, because this scale here is just in solar units. In any case, this corresponds to dim stars down here. I'm sorry, I apologize. It's late. I forgot that we have dim stars down here. I momentarily forgot about that. Sorry, I mentioned that it's negative down here. It's actually positive numbers down here and negative numbers up here. So if you have an HR diagram where the vertical axis is measured in absolute magnitude, that scale we mentioned earlier, then the negative numbers will be up top and the positive numbers will be on bottom. Sorry for messing that up, for goofing earlier. Remember, negative absolute magnitudes correspond to very bright objects. So this is dim down here, and this is bright up here. Let's talk about the different kinds of stars that are on this diagram. The first thing I want to mention is that the typical run-of-the-mill stars that are in their normal lives, they're middle-aged stars, are in what's called the main sequence. These are your standard stars that are in what we call hydrostatic equilibrium. We talked about that when we did the sun in lecture 5, the previous lecture. And the sun is a good example of a star like that. The sun is almost right in the middle of the main sequence. The sun is a middle-aged star that is in hydrostatic equilibrium, it's not just being born, it's not dying, so it's in the main sequence. Stars that are very tiny but very hot are typically called white dwarf stars. These stars are near the bottom left of the HR diagram because these stars have high temperatures, but they're very small, so they're actually relatively dim. But they're brighter than red dwarfs, which are down here. I'm doing everything in red here. Sorry, I'll get rid of this. They're brighter than red dwarfs, which are all the way down here, which are small stars, but they're cool. So they're even dimmer than white dwarfs generally. In astronomy, we're very literal. A dwarf star is a small star. Then we have the giants. The giants and supergiants. The distinction is not so important for our purposes, but giant stars are very large, and these are stars that are, as we will learn later, ending their lives, basically. These are stars that have lived and burned their fuel, their hydrogen, and they're toward the latter end of their lives. The very hottest stars are the O-type stars up here. These are very hot and very large. You should know the basic components of the HR diagram, which are what I just mentioned. So you should know the main sequence stars. You should know the top right stars are the red giants. You should know the top left stars are the high luminosity, large, hot blue giants. These are the O-type stars. Those are the ones that are in that extreme top left corner that are the most luminous. And then we have the ones at the bottom left, which are white dwarf stars. And then finally, the bottom right, which are the red dwarf and also brown dwarf stars. I forgot to mention that. The brown dwarf stars are way down here. Those are the LNT type stars, which are extremely dim indeed. This is the HR diagram. I want to show you a couple other depictions of the HR diagram and talk about some of the different components, again, of the diagram, different stars that are on there, just to emphasize. So these two figures here are both depictions of the HR diagram. The only difference is that they have some different stars on them, and the only reason they have different stars on them is because the authors wanted to label the stars. And so if you have vast numbers of stars in a diagram, it's hard to label them. So here, the authors have labeled a lot of main sequence stars as well as the red dwarfs down here. So for example, you can't see this now. So for example, Barnard star, we came across this earlier, is a red dwarf all the way down here. The sun, I mentioned this earlier, is right in the middle of the main sequence. We have other main sequence stars like Alpha Centauri, Sirius A, Altair, etc. Then we have some white dwarfs like Sirius B. And then on this diagram over here, we have, again, it's the same diagram. They're just listing different stars. We have some blue giants like Rigel. Canopus is up here. We have some red giants. Here's Betelgeuse all the way up here. And then we have some main sequence stars that are listed. I mentioned to you that along the horizontal, there's a temperature axis. I didn't actually spend too much time emphasizing this. I did mention that these are hot stars, these are cool stars. Hopefully it was clear that this is hot, this is cool, right? Blue means hot, red means cool. But I want to emphasize that the fact that hot stars are on the left and cool stars are on the right also means that the horizontal axis corresponds to the spectral classification. O-type stars are to the left because those are the hottest, and M-type stars, M, L, and T, are all the way over to the right. I did mention that O-type stars are all the way up here. Let us finally talk about the mass relationship just very quickly, and then I'll end this lecture. So for the main sequence stars, there's a relationship between the luminosity and the mass. And it doesn't really so much matter what it is, but the point is that the stars that are up here are the most massive, and the stars that are down here are the least massive. And maybe that's not terribly surprising because the stars up here are more luminous than the stars down here. Remember, this is a luminosity scale, so this is dim, this is bright. And we know that in general, the brightest stars are the hottest, but also the largest. And if a star is really large, it has a lot of mass. So all I really want you to know is that the more massive stars are near the top of the main sequence curve, and the less massive stars are near the bottom. That's it for this lecture. There was a lot of stuff in this lecture. We talked about how to classify stars. In particular, we talked about the stellar spectra classification, the O through M and then LT scale. Before then, we talked a little bit about stellar parallax. We then talked about how we categorize, not categorize, but how we conceptualize the brightnesses of stars based on the luminosity and apparent brightness. The luminosity we usually measure with the apparent The luminosity we usually measure with the absolute magnitude scale. The apparent brightness we measure with the apparent magnitude scale. And then I talked about how we categorize stars on an XY plane, a two-dimensional plane, a piece of paper, and that's called the Hertzsprung-Russell diagram. I hope that this lecture has been interesting, and at least it's been long. Thank you for watching, and I will talk to you in another video.